Okay, welcome to geometry, GADEPS, geometry, arithmetic, and differential equations of periods. Today we have Maria. How you pronounce your name?
I know
Gioia
that it's hard for
Cifani.
you. It's Gioia, like joy in
Gioia.
Pietro. Gioia,
Maria
perfect.
Gioia Cifani is going to talk about reconstruction of curves from their Hodge class.
Thanks
Uh,
for inviting me. This is a joint work with Pietro Pirola and Enrico Schlesinger. It's right here, and so if I forgot, I just say now. And in the title, as the title say, I will focus on curves. I won't be precisely now. Just want to chat a little bit of something that I think on what maybe you're more expert than me, actually. Um, but the problem is more general. So I want to set the situation in general because it's really interesting, but we can do many computation and examples in the case of curves. So we start with a complex algebraic smooth hypersurface. We do not need the dimension to be even, but we use it just to be to have easier notations. So we set the dimension to be to n, and it's an hypersurface, so it is in p to n plus 1, and we set the degree to be x, to be d, of degree of x to be d. We will use an important theorem of Griffiths that there exists an isomorphism. I won't be precise now. This is a theorem of Griffiths. I will say Griffiths plus many others because Griffiths worked a lot on infinitesimal variation of Hodge structures with many others, but this is one of the results. It is due to Griffiths. Between the primitive cohomology in every degree of subvarieties, primitive cohomology classes of X with the Jacobian ring, the certain degree of the Jacobian ring. I won't be precise now of the Jacobian ring of X. Okay. The key point is that cohomology classes of X, primitive, okay, but cohomology classes of X can be represented by polynomials. That is the great tool of this isomorphism, so easier things to handle with. What is the Jacobian ring, just to know, is just what you expect, the polynomial ring mod out, but later 2n plus 1, mod out by the Jacobian ideal, that is degree by degree. That is what we expect to the ideal generated by the partial derivatives of the equation defining x. Derivatives of f, where x is defined by f, the equation, where we expect with Jacobian. Here we use what I said before. We choose x to be smooth, so that this is an Artinian-Goresan ring. And I think that is a theorem. It was studied by Macaulay. But the important thing here is that we have polynomials here, and whenever we fix x, we can control all the Jacobian. We know x, we know the equation, we know the partial derivatives. So here we know everything, and polynomials here defines something more less comprehensible. They are Hodge classes. Okay. Which case we will use curves in surfaces. So in general, hypersurface of dimension n, this is because we use 2n with x to have easier notation here. So subvarieties of dimension n, whose class is whose Hodge class is in Hn of x, and the primitive classes, Griffiths theorem says that they are this is the degree of the degree m of the Jacobian ring in which we want to have our polynomials. So this was wrote down by Jose Movasati and SertÃ. Correct me if I'm not. I think for the first time, write down in this way, so we can associate it to a class, an ideal. They define this ideal inside the Jacobian ring. Okay, and this is in this way we can use this ideal that has some properties. They define this ideal using periods, so they writing down all these things using periods. I today will present the same construction in a different way, in a more algebraic way. So I will define this ideal as like bit. This is the same, but some a bit different way because it's more purely algebraic way. But they are the same, so they define an ideal inside the R of X that has two important. There's one for them important properties that contains the homogeneous. Sorry, I wrote down C. It should be a Y. The homogeneous ideal of Y. So the word reconstruction in the title is all in this observation that we will prove later for curves. So they asked to be not precise when we have equality. Equality here. Meaning equality, we have to fix a degree. So we have to fix a degree m, maybe in n, better, because otherwise we want really equations. So we fix a degree and we look for conditions for which we have this equality here of the polynomials defining these two things. Okay, so reconstruction means this. What we expect if you want the smartest, let's say, choice for m is the minimum degree in which the ideal is generated. And we will always refer to this m when we speak about the reconstruction. Okay, we will always speak about this. We do not write down every time these things, but degree by degree we can look for conditions to have the equality. Okay, so we can, if we are able to compute this ideal, we can reconstruct all the equation defining this variety. What we expect that the answer, let me very very imprecise, should be true when the degree of x is greater than the degree of the sufficiently larger than the degree of the subvariety. This is true for curves. For instance, this is the right answer for curves. Firstly, Griffiths and Harris showed that something like this, they do not write down any bound, just in the proof they say that something that must vanish, they do not write down any bound, but they say when C is general in moduli, the curves in surface is here n is equal to 1 in moduli, then we have something like this. We have then the degree of x should be sufficiently greater than the degree of the curve. We have exactly the reconstruction from the periods. And also I cite something like our work where we use C every curve, let's say, and we found a bound not sharp, like this bound here, not sharp, but I will write down the bound later, there are sharper bounds in some special cases in which we can do better computations. But in general, we can have a bound, maybe not sharp, but we can always find a bound. But the point is that we expect that from fixed subvarieties, if the degree of the hypersurface is bigger enough, we have reconstruction. So the question that made Movasati and Sert is interesting. Correct me if I'm not seeing something if I'm saying something wrong. But I read your question of perfectness like what can happen when the degree is lower. So we expect that for the degree of x to be greater enough, we have reconstruction. What we can recover when the degree of x is little, whatever it means, they make this definition of perfectness. So a class y always in Hn, and this could be also more general. I just use this special case of subvarieties of codimension n in dimension 2n, but this could be more general for HPQ. A class is perfect if there exists, so we do not have a degree m, we do not have the equality, so we have something more here, and the point is that we want to control, let's say, what is left. And the way to control it is that we are something more, and we hope that this something more is something like this, so the homogeneous ideal of other curves that we can control. There exists other subvarieties, y1, let's say t, subvarieties in x of always codimension n, such that what we expect, so the ideal they are associated with is always the same. I will set y to be y0, and there is nothing more. The sum of the homogeneous ideals, degree by degree, okay, degree by degree, up to a certain degree. I should say here that at degree m, to be more precise, if it's true for every degree, it is perfect and stop. This is exactly E alpha y in degree up to degree m. So we have nothing more than homogeneous ideals of curves that we can control because we have this property. So if we can rewrite this property in a way to control that we can do for curves, what does it mean that they define the same ideal? We know which curves we have to check for perfectness of a class. And we can reconstruct exactly this ideal here. So the question that they ask, maybe I can write more space. The second question that we will answer, or trying to answer for curves, is: are all the classes perfect? And clearly, if not, sorry, there are too many comments. If not, give conditions for perfectness. Okay. We can do this. We can answer to this, and the answer is unfortunately no, because we have counterexamples. I will say it in a minute. This is still open. We don't know. We have counterexample, but we do not have a real condition. We do not actually say why it is not perfect. But still, this is still an interesting question to try to ask. The known cases, why they ask if all the class is perfect, because there are examples, and the first example is their example because they made the definition, but they say that they use a result of done, and partially it was also based no, but it was done for curves also that is going to be skin. And this is the case of complete intersections. Complete intersections are subvarieties, are perfect classes. Maybe sorry. Doesn't matter. They are perfect. I will spoiler. We did something more. We generalized this in the case of curves, so we always work with n equal to 1, so it is more general for every n. In complete intersection perfect classes, this is quite easy to write down. But for curves, we can do more. Complete intersection are a particular example case of arithmetical and Macaulay curves. So we can prove that arithmetical and Macaulay curves are perfect classes. So the class is more general. The set of perfect classes is bigger, and it is due with a work of Alice Green and Peskin. We will see later. But no, I said before, because there are counterexamples. Examples. We found out just one counterexample, but I will bet that there are many other counterexamples in the realm of rational curves, out of the realm of rational curves. I don't know. There is this counterexample. Our counterexample is C is a quartic curve. Is a quartic curve, smooth and rational. Inside a surface, now I write S, but is always X. That is again a quartic now surface. Smooth always, because our hypersurfaces are always smooth. And this is not perfect at degree 3, that is the degree in which the ideal of the quartic is generated. But it is perfect at degree 2. So the perfectness depends, all these definitions depends on the degree in which we are asking, we are looking our ideals, our polynomials. So for me, if I do not say something different, the degree is always the degree in which the ideal is generated. In this case, it's 3. But for instance, this is perfect at degree 2. Inside this surface. So all these things are related with the degree of the surface or the hypersurface containing the curve, the degree that we choose. So they are choose to make, and then we can say if it is perfect or not, if we have reconstruction or not. Okay, so it is open always the case. So we will see in a more deep way how we can compute. And I will say this is the case. Many of these things comes from the work of Alice Green and Peskin, that write down all these things to study the Nether-Lefschetz loci. This is actually, they presented it as this is actually the algebraic version of the Nether-Lefschetz loci problem. I don't know how to say it. but they really want just to write down the algebraic version. They do not prove anything more. So the work of Alice Green we cite is really hard to find also in the literature. But it's very deep, very useful for us because it makes it gives us a way to make computations in examples. So I will present. I will left periods more to you, and I will present a more algebraic version of all these things. Also, we are in a toy case with the curves and surfaces in which we can rewrite, and we will do it because it will be a bit easier for us. That it should be an S. It doesn't seem an S. We will rewrite this isomorphism here, starting from the cotangent bundle sequence. So OS minus D is always the degree of S is the X before, and C the Y before, to the omega 1 of P3 restricted to S to omega 1 of S. So taking cohomology, we have here H1 omega 1 P3 restricted to S. It is generated by the class of the hyperplane section. I just write H, the hyperplane section class. Here we have H1 omega 1 of S. And here we have, maybe I'm to H2 OS minus D, that is dual to H0 OS to D minus 4 dual. And we're almost there because it is H2O P3. If we want to put out by the equation of S, we can write OS in degree 2D minus 4 quotient by the Jacobian of S in degree 2D minus 4. So we are almost there. Okay, let's give a name to this map. And here we have our class. And we can associate to our class alpha C in this dual. This dual means that it is a linear map from H0 ORS to D minus 4 to C. This is a linear map here. Okay, we can think of the hyperplane class here going to the hyperplane class restricted to S, and we can here think of quotienting by this class. And this is exactly H1 OS primitive orthogonal to the hyperplane class. So maybe I want to, if I'm able, want to move it. So here, if we take H1 OS and we quotient by the curve alpha, we have exactly H1 omega 1 OS primitive, so the primitive classes. And it is clearly isomorphic to the image. And the image, if we consider the dual of this alpha going from sorry, on the image. We can compute the image of alpha dual just considering alpha dual going to H0 as 2S minus 4, it is self-dual to H1 of 1 OS, and the curve is exactly the Jacobian because it is the image of H1, H2 of 1S. So the image of alpha is exactly the R to the minus 4. This using the dual of alpha. So it is exactly a way to reproduce the isomorphism of Griffiths. And it tells something. It tells that when this class is 0, for instance. So, okay, we define. Okay, we have the class, so we have this alpha c. Inside here, we define E alpha c, our ideal, as the annihilator of this alpha c. That, if you want, is are the element in each 0 OS. Okay, degree by degree. Maybe I'll write m for the degree. OS of m, such that alpha c f times g is 0 for every, like the kernel at some degree, in the dual of it. So H0 as, maybe I'll write so. In the dual 2d minus 4 minus m. The product goes to 2d minus 4, and then we apply alpha to go to 0, the kernel of alpha. So the annihilator of this alpha c is exactly our idea, that we can define also as they say, as they did with periods. And we have properties. We have the, like another Lefschetz properties. The alpha c is 0 if and only if c is a complete intersection. Because the kernel of alpha is exactly something that is this comes from the hyperplane section. And another thing, important thing that we can prove from the way we define this isomorphism and this sequence is when two curves define the same ideal, and we will use it later. If and only if there exists and maybe I'll there are too much m and n, s, t, and p, with st non-zero and relatively prime, such that we have this property ph plus sc plus td is linearly equivalent to 0. So they should be related by something that is almost a liaison between T and D and H. So if we look for other curves for perfect for the perfectness of a class, we should look for a relation with like this. Okay.
Maybe one observation that you can write down everything here over a field of arbitrary characteristic and not necessarily algebraic closed, because this would be necessary for construct if we want to do this story. Okay.
Yeah, sure. Sure. This is purely algebraic. This then depend that the fact that we're working in C. No. Thanks. Okay, going further, what is really useful for the work of Alice Green and Peskin is something like a computational way to use all these things, because we really want to, let's say, compute or work with this ideal. And the way we can do it is start from the normal sequence of C in S. This is an omega because someone told me that it seems W, but it should be an omega. So omega C of degree 4 minus D, and the normal bundle of C, and the normal of S restricted to C, so CD. Here, if we twisting by minus D and taking cohomology, I'll try to write down more things. Yeah. Here we have H0 degree by degree. This with every degree. of the normal of C in degree minus D and goes to H0 O C, and H1 of omega C degree 4 minus 2D. It is the dual of OC, H0 OC in degree 2D minus 4 dual. So we can do as before, we can take the one here and send the one here into a linear form here. So as before, it goes from the H0 C in degree 2D minus 4 to C, or to K if you want. And this beta C, this is a proposition, the key proposition of Resgrande Peschina is that it is, sorry, for too many, that alpha C before is the pullback of this beta C, where pi is the map sending H0 O as degree by degree to H0 O C. So it's the pullback to S of this form beta C. And I write down here also, I will say as before, beta, this map here, because we can, as before, define the annihilator of this linear form. And by the diagram, it is exactly, if you write down using the exactness of the diagram, the definition, it is the image of this beta here. So we can really use this diagram, and maybe I'll try to rewrite here. Here we have H0 OS, H0 OC. This is pi. H0 of the normal bounded is pi minus D, and it is beta. So this is the key point, and the other other things that we have from these is that level. If we take the annihilator of beta C and we take pi minus 1, this is just in general contained in the annihilator of alpha. And the quality, if and only if pi is surjective. Okay. Actually, maybe I'll take more space. Actually, I will make some remarks. Pi surjective is equivalent to say that C is an arithmetico-Macaulay curve. This is mostly the definition. One of the definition of an arithmetico-Macaulay curve is pi surjective if you want that the sum over program H1 or is 0. Every H1 or SE is 0, meaning that pi is surjective. But this is so we will say that we have equality if and only if C is an arithmetico-Macaulay curve. That actually is true, but to be precise, this is this is weaker, because we have just to check surjection for degrees from 0 up to 2D minus 4. So it is a little weaker than being arithmetico-Macaulay, but actually I don't know an example of something that is not arithmetico-Macaulay but has all these degree, pi surjective in all the degrees. What happens in general, just to, if you're not used to it, in general, so general meaning not ACM, pi is surjective at some degrees, and not in others. So there are degrees in which pi is surjective, so there are degrees in which we have equality, and there are degrees in which we do not have equality. So fixing a degree in which we want to look for I don't know, perfection reconstruction, means also checking this property can change by changing the degree. So we really have to fix the degree in which we want to look if the pi is surjective or not. If C is an SCN curve, we are sure that it is always surjective. And with this, we can also recover the properties before in a really easy, I'm checking the time, a really easy way. I will rewrite here the diagram to make it easier to follow, because I know that one can lose and is twisted by minus d and is pi. So the homogeneous ideal of C is the kernel of pi, because here we have H0 of the ideal. So we are of the homogeneous ideal of C. So it's the kernel of pi. So it is clearly containing pi minus 1 of the image of the annihilator of beta, of the image of beta. So it is contained in a alpha C, because it is contained in this pi minus 1 of the annihilator, because it's pi minus 1 of 0. And moreover, here, if we we complete here the image of H0 of the tangent of, I don't remember, twisted by minus d, has image that its image here is the Jacobian inside the H0 of S, saying that the Jacobian of S is also containing alpha C. I want to stress this point, but it's not important for us, just because in the way we define all these things, it is not clear that the Jacobian is already inside our ideal, because the ideal defined in this way, it lives inside H0 P3, or if you want H0 OS, if we mod out by the equation of S. Actually, we have to do something more, because if it contains the Jacobian, we can think of this ideal. I won't change notation in order not to make it too heavy, but I will. You can think this ideal already in the Jacobian ideal, because the Jacobian ring, sorry, because it contains the Jacobian ideal, so we can quotient by the Jacobian. In the way the Movasati and Sert define it, they already define it in the Jacobian quotienting by this ideal, but this is the same. And we're happy that it contains the Jacobian, so that we can think to quotient by this element here. This is the important thing, and now it's clear how to produce it. It is the kernel, so it should be there should be an equality here. So conditions. We're looking for conditions for equality. Always we fix an M. So we want that this is equal to this, and we have two steps to make it. The first step is that we want equality at this level. Otherwise, there is, because pi minus 1 of 0 is like inside here. So we want equality at this level. Equality at this level means that pi is surjective. Pi surjective in degree m means we should check the dual, let's say, the dual degree means that each one of the ideals in the dual with respect to 2 minus 4 degree is 0. So pi in this degree is surjective. And this tells you that there is equality at this level. And then we want that this is exactly the kernel of pi. So the image of beta should be 0. The image beta should be 0, and we ask that sufficient conditions. Maybe H0 of the normal bundle of C in degree m minus d, because we fix an m, is 0. So these two conditions gives you a bound, not in general sharp, are sharp bound of the type that the degree of S, that is D, is sufficiently greater than the degree of C or other invariants related to C, not only the degree we will see, but invariants to C in general. And gives you can write down, and this is a bound. There are sufficient conditions. Clearly, this condition is verified when we look for Hessian curves. So for Hessian curves, we can do better because we can exactly write down when the H0 of the normal bundle vanish. And this is exactly what we did. After. So in the case of arithmetically Cohen-Macaulay curves, I just want to write down the correct number. If I find it, okay. So E, as I said, it is not only the degree. We have to use the index of speciality of the curve for an Hessian curve, that is the minimum of n for which each one of n is not zero. And we will set sigma to be the minimum degree of a surface containing C, so the minimum for which the H0 of the ideal is not zero. And I will write down that here our M is E plus 3. That is the degree, the minimum degree in which the ideal of the ACM curve is generated. And here we can find a bound of this type 2E minus sigma plus 8. And this is a bound, you know, that is degree sufficiently greater than this. Maybe we can make an example that I was talking about before with saying that the case of the twisted cubic. The twisted cubic is the only rational curve that is also an Hessian curve. And here they proved that for D greater or equal than 5, we have reconstruction. I always speak about the degree. And they do not know if we have reconstruction in degree 4. They tested, they brought down a computer program, a code testing the periods, computing periods, and they tested on random twisted cubics and quartic surfaces, and they always find out that they were perfect. They were the same. They have the right dimension of the things, and actually with our bound D equal to 4, if you write down the numbers here, this is 4 for a twisted cubic. So D equal to 4, we have a reconstruction. Okay. So this is slightly better than this 5 that they found by hands. This is actually 4. So we have reconstruction. We can do also because if you want H0 of the normal bundle, then degree minus 2 is 0 in this case. Or if you can compute it, you can compute it. So one can ask to go a bit further than this, because ACN curves are a good space to compute things and to test things. Sorry. And okay, we can do further. We can go further. So maybe the most important result is okay. That ACN curves actually are perfect. So we can fill all the cases, not only with the one in this bound. ACN curves are perfect. are perfect classes. So the class of an Hessian curve is perfect, to be more precise. I want to just to give a hint of the proof. Sorry, I was writing in Italian. A sketch of the proof, just to say what we use heavily. We use heavily a proposition of Ellis-Guernet-Peskin that has an hypothesis that C should be an Hessian curve. And then we can exactly describe this element here, degree by degree. We can exactly describe how it is made, because we have a surjection here of the sum over M of H0. Sorry, I don't want to. Okay. H0 OS in C plus. Okay. No, there are too many M. Sorry, there are too many M. Let's say yes. S plus M H and H0 O C minus C minus SH. Okay, the point is that they do not prove this proposition, because they say that it is clear. Actually, it is really unclear for me still. The real point here. So we tried a bit to check if we can reverse, because if C is an Hessian curve, then we have this description, and we tried a bit to recover if it is true this or not. But it's really, really hard to understand how they prove these things, because they didn't write anything in their work. Actually, it should be probably the key point to understand better the perfectness, to trying to understand how they did all these things. But the point in which we use it is that these two things are not, the sum is finite here, because they are non-zero for a finite number of S here. So we have a finite number, and if we fix one of these elements of the finite sum, and we take an element in this linear system, something like something made like this, then we have that these things here can become something like the ideal of the element. We choose the homogeneous ideal in degree M always, of the ideal of D inside S. So the sum, the ideal of alpha C, so our ideal is exactly, we can exactly write down as a finite sum of pieces like this. This is exactly what we want. So the perfectness. And I stress also that something of this type is exactly something that has, alpha D, that defines exactly the same ideal of C. So these the curves of this type are exactly what we're looking for. And when we write down the element here, we have just the homogeneous ideal of the curve C, and curves made like this. So perfectness, as we defined before. So the question now could be, the open question could be,
maybe one question. So you need just another extra curve D, or there are more curves?
No, there are more. Actually, we do not tested many examples of Hessian curves, the twisted cubic, okay, but there are more actually. No, could be more than one. I'm just saying that they are kindly all of this type, and this type is the one we're happy to have. No, there could be more.
Okay.
when we try to write down examples of the ACN curves before proving it, the key point for me, that I'm not really an expert of ACN curves, is that all the ACN curves are related with liaison to another ACN curves, and they're all related to a line. This is one of the definition of the ACN curves, and the curves you find out when you look for perfectness by hand, for the curves satisfying the property by hand, is exactly one of the things that they related to by geometric property of ACN curves. So maybe it's easier if you look for an example to not to compute it by trying to use the geometry of what you know from the curve. But at least from a theoretical point of view, here you can have more. And actually, it should be true that they are all ACN, but it's not important. I'm not sure that it's always true, the curves you find here, but you can find more than one. Yeah. So one of the questions, at least for me, is that if are ACN curves the biggest class, I don't know, of perfect curves. We don't know. Actually, I think in the realm of rational curves, I'm pretty sure that it's hard to find examples of curves perfect in every degree, maybe in some degree, but not in other. But away from these two big sets of examples, really, I don't know. It seems that it seems to us that actually this proposition could be inversed, but we didn't manage to do it. So I don't know. Okay, our counterexample. I have 10 minutes left. I just want to just computation. Why rational curves? Rational curves because we can do computation. So it's you have to be able to compute these two things: the normal bundle and this H1 of the ideal. You have to be able to compute by hand the numerical the things invariants of the curves. Irrational curves, you can do it. General rational curves better for the normal bundle, but in this case, for instance, the normal bundle of C is 2 copies of O7 or C7. So one can really compute by hand the rational, all the vanishing of these things. So if you compute by hand the vanishing here, you have that our bound tells you that if the degree of the surface is at least 5, you can reconstruct. Here M is 3 because the homogeneous ideal is reconstructed at degree 3. So there is only one quadric containing C that is also smooth, but you need cubics to define C exactly. So the question is, what happens in degree 4? So C is containing a smooth portic surface. Okay, so we have the E alpha C in degree 3 that we can compute it as dimension 16. We can compute it using also, if you want, here you can also use that dimension that is easier to compute. In this case, too many parentheses. 3. This is 15, and this is enough for us. But actually, we computed the exact dimension using the fact that the ring that you actually Alice Grande Peskin, I write just to let you know, define this ring, the sum of HOS degree by degree, this n, moved out by this alpha. They define this, and this is also an Artinian Gorez ring. So the property is that you can there is a pairing here. The maximum degree is 2d minus 4. So there is a pairing here, and we use the pairing to compute better this dimension. But actually, this is computable by hand, and this is enough in this case. So inside here, we have the homogeneous ideal of, let's say, dimension. We have the homogeneous ideal in degree 3, that is 7, and there are 7 cubics defining in the homogeneous ideal of C. And as we define the things, we have to consider also the Jacobian. Otherwise, we have to mod out all these things by the Jacobian. This is not important, but and this is 4 because S is degree 4, so we have 4 independent cubics. They are the partial derivatives of S, of the equation defining S. And then we have to look for curves D such that, let's say, PH plus SC plus TD, maybe I write it is linearly equivalent to 0. And we made computation really by hands here. So our algorithm, let's say, is not really extendable in general because the computation are easier because we have degree 4. When we were the degrees less easy, a computer can do it, but not for every degree. So we just stopped at one counterexample, but for at least general quintic success should be also other counterexample. We just take this thing here, and we made the system given by the dot, the intersection with H, with C, and with D. So we have a system, a homogeneous system with the unknowns that are H times H dot D, C dot D, and D square are unknown. And we look for solutions D and some numbers of D. They are solution of this system given by, and we also have parameters PS and T. They are parameters. This can be done by hands. We did it, but also one can write down a computer program because it's homogeneous with these unknowns, a homogeneous linear system. And the only, so maybe I'll write here, the only example that we found, there is only one D, clearly different from C because this is a trivial solution, is D, the numbers tells you that D is, again, another quartic rational curve. And this quartic rational curve from the geometry of the situation should be the quartic given by the quadrant containing C, cap S containing C and D. So the other component of the intersection of the quadric with S. This is degree 4, this is degree 2, and those are degree 4. So we have to add here, and there is nothing more. So here we have to add the homogeneous ideal of the cubics in the homogeneous ideal of D, but I won't be precise here. Here we do not have 7, just because we have to consider the intersection of the cubics containing D with the cubics containing C. And there are 4 cubics in the intersection, because whenever we have a cubic containing the quadric, it contains both. So we have 4 cubics containing both, so it is 3 left. So here we have 14, at most 14, because we are not checking if one of these, for instance, is already containing C or D. So at most it is 14, but it is not enough even for the pi-1 of the annihilator, but this is just an observation. It is really big, lower than 16. So we have at least 2 independent cubics that are in this ideal, but did not define, the Jacobian, the curve or other curves related to C. So another interesting question could be, they clearly define something, how it is related to C, if it is related to C, or what are saying to us those cubics we really don't know. On C, maybe nothing, but in general, I don't know. And I can stop here.
Okay, thanks, Maria. Usually, I think, I don't know if clapping the hand in the online seminar is good or not. Anyway, maybe I will stop recording and I will ask
Yeah.
for